Before there were clocks, before there were calendars carved into stone, there was only the rhythm of the world itself. The earliest humans did not measure time as we do now, with numbers and divisions. They felt it instead, in the warmth of the sun climbing the sky, in the silver arc of the moon growing full and then fading, in the patient turning of the seasons. The day was the first unit of time that human beings truly understood. It arrived with light, it departed with darkness, and this simple alternation was perhaps the first pattern our ancestors recognized as something that could be counted. But the day itself was not uniform. In the tropics, where early humans first walked, the length of daylight remained fairly constant throughout the year. In the higher latitudes, the days stretched long in summer and contracted to brief windows of light in winter. Moving beyond the day, the moon offered another measure. The lunar cycle, lasting approximately 29.5 days, gave shape to something we would later call a month. Ancient peoples across every continent watched the moon wax and wane, and they found in this celestial clock a way to mark time that extended beyond the immediate rhythm of day and night. The word month itself descends from the word moon in many languages, a linguistic echo of this ancient connection. Consider the Babylonians, who lived in Mesopotamia between the Tigris and Euphrates rivers more than 4,000 years ago. They developed one of the first sophisticated calendar systems, dividing the year into 12 lunar months. But they faced a problem that would puzzle many ancient civilizations. The lunar year, consisting of 12 cycles of the moon, is approximately 11 days shorter than the solar year, the time it takes for Earth to complete one orbit around the Sun. To solve this discrepancy, the Babylonians occasionally added an extra month, a 13th lunar cycle, to keep their calendar aligned with the seasons. This practice of intercalation, as it came to be known, represented an important conceptual leap. It showed that ancient peoples understood time not just as something that happened to them, but as something that could be adjusted, managed, and organized according to human needs. The Egyptians approached time differently. Living along the Nile River, they organized their year around the flooding of this great waterway, which brought fertile silt to their fields and made agriculture possible in an otherwise arid landscape. They divided the year into 3 seasons: Akhet, the inundation; Peret, the growing season; and Shemu, the harvest. Each season contained 4 months of 30 days, with 5 additional days added at the end to total 365 days. This Egyptian calendar, developed around 3000 BCE, was one of the first solar calendars, tied not to the moon, but to the sun's annual journey. The Egyptians also divided the day and night into 12 hours each, though these hours varied in length depending on the season. A summer daytime hour was longer than a winter daytime hour because there was simply more daylight to divide. In ancient Greece, time became a subject of philosophical contemplation. The pre-Socratic philosopher Heraclitus, who lived around 500 BCE, famously observed that one cannot step into the same river twice. What he meant was that time ensures constant change. The river is always flowing, always different, and so too is the person stepping into it, transformed by the passing moments. Heraclitus saw time as a kind of fire, always consuming the present moment and creating the new. For him, reality was not a collection of static things, but a process, a constant becoming. This view stood in contrast to his contemporary Parmenides, who argued that change was impossible and that true reality was eternal and unchanging. Time, for Parmenides, was perhaps an illusion, a mere appearance that distracted from the unchanging truth beneath. Plato, writing in the 4th century BCE, offered another perspective. In his dialogue Timaeus, he described time as a moving image of eternity. The eternal realm, which Plato called the world of forms, existed outside of time, perfect and unchanging. The physical world we inhabit, by contrast, unfolds in time, which Plato saw as having been created along with the cosmos itself. Time, in this view, was not something that had always existed. It came into being when the universe did. Aristotle, Plato's student, took a more empirical approach. He defined time as the number of motion with respect to before and after. In other words, time is how we measure change. Without motion, time would have no meaning. Aristotle also grappled with paradoxes of time. If the present is merely the boundary between past and future, and if past and future do not exist in the present, then does time exist at all? Across the ancient world, in India, philosophers and religious thinkers developed their own concepts of time. In Hindu cosmology, time is cyclical rather than linear, operating in vast cosmic cycles called yugas. The current age, the Kali Yuga, is considered the age of darkness and discord, but it will eventually give way to a new cycle of creation. These cycles repeat endlessly, with the universe being created, existing, and then dissolving, only to be created again. The Buddhist tradition, which emerged in India around the 6th century BCE, took a somewhat different view. While acknowledging cycles of rebirth, Buddhist philosophy emphasizes impermanence, the idea that all conditioned things are constantly changing. Time is not seen as a container in which events occur, but rather as something inseparable from the processes of change themselves. Meditation practices in Buddhism often focus on experiencing the present moment fully, recognizing that past and future are mental constructs. In ancient China, time was understood through the lens of agricultural cycles and celestial observations. The Chinese developed a luni-solar calendar that combined lunar months with solar terms, dividing the year into 24 periods that marked important agricultural events. These periods had poetic names like Awakening of Insects and White Dew, connecting time to the natural world in intimate ways. Chinese philosophy also contributed unique perspectives on time. Confucianism emphasized the importance of proper timing in human affairs, the idea that there is a right moment for action. The I Ching, or Book of Changes, one of the oldest Chinese texts, is fundamentally about understanding and navigating the temporal dimensions of life. Time in this tradition is not merely chronological, but qualitative, with each moment possessing its own character. The Maya civilization in Mesoamerica developed one of the most sophisticated calendar systems in the ancient world. They actually used multiple calendars simultaneously. The Tzolk'in was a sacred calendar of 260 days, used for religious purposes and divination. The Harb was a civil calendar of 365 days, divided into 18 months of 20 days each, plus 5 days considered unlucky. But the Maya also tracked much longer cycles of time. Their long count calendar, which began on a date corresponding to around August 3114 BCE in our calendar, measured time from a mythological creation date. This calendar moved through cycles of increasing length. Kin, days; Winor, 20 days; Tun, 360 days; Katun, 7,200 days; and Baktun, 144,000 days. The completion of cycles held great significance in Mayan thought. When 13 Baktuns were completed, a great cycle ended, and the universe underwent a form of renewal. This would occur again on December 21st, 2012, in the Gregorian calendar, leading to much speculation in modern times about what the Maya believed would happen. In truth, they saw it as the end of one cycle and the beginning of another, part of the endless rhythm of creation. Ancient timekeeping devices reflected the desire to measure portions of the day with greater precision. The sundial, which casts a shadow that moves as the sun travels across the sky, may have been used in Egypt as early as 1500 BCE. These devices divided daylight into hours, though, like the Egyptian temporal hours, these measurements expanded and contracted with the seasons. Water clocks, or clepsydry, offered a different solution. By allowing water to drip from one container to another at a steady rate, these devices could measure time even when the sun was not visible. The Egyptians, Babylonians, and Greeks all used water clocks. In Athens, water clocks were used to limit the time allowed for speeches in law courts, ensuring that proceedings did not stretch on indefinitely. The ancient Romans inherited and adapted many of these timekeeping methods. They divided the day into 12 hours and the night into 4 watches, each lasting 3 hours. Roman hours, like those of earlier civilizations, varied in length with the seasons. It was not until much later, in the medieval period, that the idea of hours of equal length throughout the year would become standard. Consider also how ancient peoples marked the longer rhythms of time through monuments. Stonehenge, constructed in several phases between 3000 and 2000 BCE, aligns with the summer solstice sunrise. On the longest day of the year, the sun rises directly over the heelstone, creating a sightline that connects celestial and terrestrial realms. This alignment suggests that Neolithic peoples were not merely tracking time, but ceremonially acknowledging their place within cosmic cycles. In ancient cultures, time was often personified or deified. The Greeks had Chronos, sometimes confused with the Titan Kronos, representing the inexorable march of time. The Romans knew this deity as Saturn. In Hindu tradition, Kala is both time and death, reflecting the understanding that time brings all things to their end. Time was not neutral or abstract, but a force with agency and purpose. The very language ancient peoples used to describe time reveals their conceptual frameworks. In ancient Greek, there were at least 2 important words for time: chronos and kairos. Chronos referred to sequential, quantitative time, the kind that can be measured and divided. Kairos, on the other hand, referred to the right moment, the opportune time, qualitative rather than quantitative. This distinction acknowledged that not all moments are equal, that time has texture and significance beyond mere duration. As ancient civilizations grew more complex, the need for standardized timekeeping increased. Agricultural societies needed to know when to plant and when to harvest. Religious ceremonies required precise scheduling. Administrative systems needed ways to record and coordinate events. Time, which had once been simply the backdrop of life, became something to be managed, regulated, and controlled. Yet even as time was increasingly quantified and measured, ancient thinkers recognized its paradoxes and mysteries. How can time pass if the present is just an infinitesimal point between past and future? If the past no longer exists and the future does not yet exist, what reality does time possess? These questions, first posed thousands of years ago, continue to puzzle philosophers and physicists today, suggesting that the nature of time remains, in fundamental ways, as mysterious as it was to our earliest ancestors watching the sun rise over an ancient horizon. When Isaac Newton sat down to write his Principia Mathematica in the late 17th century, he began with definitions. Among them was his definition of time: absolute, true, and mathematical time. Of itself and from its own nature, flows equably without relation to anything external. What Newton meant was that time is like an invisible river flowing at a constant rate, unaffected by the events that occur within it. A second is a second is a second, whether measured in an empty room or on a speeding train. This view of time as absolute and universal seemed intuitive. It matched human experience. When we look at a clock, we assume that it measures something objective, something that exists independently of the clock itself. Newton's framework worked beautifully for describing motion, predicting planetary orbits, and building mechanical devices. For more than 2 centuries, absolute time remained the foundation of physics. But in 1905, a young patent clerk named Albert Einstein published a paper that would fundamentally alter our understanding of time. The paper was titled "On the Electrodynamics of Moving Bodies," though it would become known as the special theory of relativity. Einstein began with a deceptively simple observation. The speed of light appears to be the same for all observers, regardless of their motion. Imagine you are standing on a platform, watching a train pass by. Someone on the train shines a flashlight forward. Common sense suggests that, from your perspective on the platform, the light should be moving at the speed of light plus the speed of the train. But experiments had shown this was not the case. The light moves at the same speed for both you and the person on the train, approximately 300,000 kilometers per second. To resolve this apparent paradox, Einstein realized that time itself must be flexible. If the speed of light is constant for all observers, then observers in different states of motion must experience time differently. This phenomenon is called time dilation. A clock moving relative to an observer runs slower than a clock at rest relative to that observer. The effect is minuscule at everyday speeds, but becomes significant as one approaches the speed of light. Consider the famous twin paradox, a thought experiment that illustrates time dilation. Imagine 2 twins, one who stays on Earth and one who travels in a spaceship at a speed close to that of light. When the traveling twin returns, they will have aged less than the twin who remained on Earth. This is not an illusion or a trick of the clocks. The traveling twin has literally experienced less time. Their heartbeats, their thoughts, the decay of atoms in their body, all have unfolded more slowly relative to Earth's reference frame. Time dilation has been confirmed through numerous experiments. In 1971, scientists placed atomic clocks on commercial airplanes and flew them around the world. When compared to identical clocks that remained on the ground, the flying clocks had indeed measured slightly less time, by just a few hundred nanoseconds. The effect was tiny but measurable and matched Einstein's predictions precisely. Particles called muons provide another confirmation. Muons are created when cosmic rays strike the upper atmosphere, about 10 kilometers above Earth's surface. They decay very quickly, with a half-life of about 2 microseconds. At their typical speeds, muons should travel only about 600 meters before decaying, meaning very few should reach the ground. Yet we detect large numbers of muons at sea level. The reason is time dilation. From our reference frame, the muons are moving so fast that time slows down for them, allowing them to live longer and travel farther before decaying. Einstein's special relativity deals with motion at constant speeds. But in 1915, he extended his theory to include acceleration and gravity, publishing the general theory of relativity. This theory revealed an even stranger property of time. Gravity affects its flow. The stronger the gravitational field, the slower time passes. Imagine 2 clocks, one at sea level and one atop a tall mountain. The clock on the mountain, being farther from Earth's center and thus in a slightly weaker gravitational field, will run faster than the clock at sea level. The difference is incredibly small, just tens of nanoseconds per day, but it is real and measurable. The global positioning system, which requires extreme precision, must account for these relativistic effects. Without corrections for both special and general relativity, GPS coordinates would drift by several kilometers per day. The effect of gravity on time becomes more dramatic near massive objects. Near a black hole, where gravity is immensely strong, time slows dramatically relative to distant observers. An astronaut falling toward a black hole's event horizon would appear to a distant observer to slow down and freeze in time, never quite reaching the horizon. From the astronaut's perspective, however, they would cross the horizon in a finite amount of their own time, though they would not survive the journey due to the extreme tidal forces. General relativity also revealed that space and time are not separate entities, but are interwoven into a single fabric called space-time. Events are not located in space and time separately, but at specific points in this four-dimensional space-time. Just as matter tells space-time how to curve, the curvature of space-time tells matter how to move. Gravity is not a force pulling objects together, but the result of objects following the curved geometry of space-time. This curvature of space-time leads to another curious consequence: the existence of gravitational waves. When massive objects accelerate, they create ripples in space-time itself, ripples that travel outward at the speed of light. These waves were first directly detected in 2015 by the LIGO Observatory, confirming a prediction Einstein made a century earlier. The detected waves came from two black holes spiraling into each other more than 1 billion light-years away, momentarily stretching and squeezing space itself by less than the width of a proton. Moving from relativity to quantum mechanics introduces yet another perspective on time. In the quantum realm, the realm of atoms and subatomic particles, many of the familiar properties of time seem to break down or become uncertain. Quantum mechanics is fundamentally probabilistic. Before we measure a particle's position or momentum, these properties do not have definite values. They exist in a state called superposition, a kind of blurred potential that only crystallizes into a specific outcome when observed. The role of time in quantum mechanics is somewhat peculiar. In the standard formulation, time is a parameter, not an observable like position or momentum. You cannot measure time in the same way you measure the energy of a particle. Time in quantum mechanics is more like the background stage on which quantum events unfold, similar in some ways to Newton's absolute time, though the events themselves are utterly different from classical physics. Quantum mechanics also introduces the concept of quantum entanglement, where particles can be correlated in ways that seem to transcend space and time. If two particles are entangled, measuring one instantly affects the other, regardless of the distance separating them. For a moment, Einstein called this spooky action at a distance and was deeply troubled by it. Yet experiments have confirmed that entanglement is real, though it cannot be used to send information faster than light, preserving the cosmic speed limit established by relativity. Some interpretations of quantum mechanics have radical implications for time. In the many worlds interpretation, proposed by Hugh Everett in 1957, every quantum measurement causes the universe to split into multiple branches. Each possible outcome occurs in its own branch of reality. From this perspective, time is not a single path, but an endlessly branching tree of possibilities, with every quantum event creating new timelines. Another approach, called quantum loop gravity, attempts to merge quantum mechanics with general relativity. In this framework, space-time itself is not continuous, but is made of discrete, quantized units. Time and space, at the smallest scales, come in indivisible chunks, somewhat like pixels on a screen. The Planck time, approximately 5.39 times 10 to the negative 44 seconds, represents the smallest meaningful unit of time in this view, the quantum tick of the universe's clock. Then there is the arrow of time, The observation that time seems to flow in only one direction, from past to future. We remember yesterday, but not tomorrow. Eggs break, but do not spontaneously reassemble. Stars shine and eventually burn out. This directionality is not explained by the fundamental laws of physics, most of which work equally well whether time runs forward or backward. The arrow of time is instead connected to the second law of thermodynamics, which states that entropy, a measure of disorder or randomness, always increases in a closed system. A broken egg has higher entropy than an intact one. Smoke dispersed through a room has higher entropy than smoke in a concentrated cloud. The universe as a whole is moving from states of lower entropy to states of higher entropy, and this increase gives time its direction. But why did the universe begin in a low entropy state? This question remains one of the deepest mysteries in physics. Shortly after the Big Bang, the universe was remarkably uniform and ordered. As it expanded and evolved, matter clumped into galaxies, stars formed and died, and entropy increased. The arrow of time points away from this initial low entropy state, but why that state existed in the first place is not fully understood. Some physicists have proposed that time might not even be fundamental. According to this view, time is an emergent property, something that arises from more basic constituents, just as temperature emerges from the motion of molecules. In certain approaches to quantum gravity, the equations describing the most fundamental level of reality do not include time at all. Time appears only when we consider larger, more complex systems. Consider also the block universe view, a philosophical interpretation consistent with relativity. In this view, all of space-time, past, present, and future, exists simultaneously as a single four-dimensional block. The flow of time, the sense that the present moment is uniquely real and that the future has not yet happened, is merely a feature of our consciousness, not of reality itself. We are like readers moving through a book that already exists in its entirety. This view challenges our intuitive sense of free will and causality. If the future already exists in the block universe, is it truly open or is it already determined? Some philosophers argue that our choices can still be meaningful within this framework, while others find the implications troubling or incoherent. The relationship between time and entropy also raises questions about the ultimate fate of the universe. In the far future, after all stars have burned out and all black holes have evaporated through Hawking radiation, the universe may reach a state of maximum entropy called heat death. In this state, no energy gradients remain, no work can be done, and time, in a meaningful sense, may cease to have significance. The universe would persist, but nothing would change. Yet other cosmological scenarios suggest different endings or even new beginnings. In some models, the universe could contract in a big crunch, the reverse of the Big Bang. In cyclic models, universes might expand and contract repeatedly, with time itself being reborn in each cycle. In theories involving the multiverse, our universe might be just one bubble in an eternal, infinite foam of universes, each with its own timeline. The study of black holes has also revealed deep connections between time, information, and thermodynamics. Stephen Hawking showed that black holes emit radiation and gradually evaporate. This process raises the information paradox. If information falls into a black hole and the black hole then evaporates, does the information disappear from the universe? Quantum mechanics insists that information cannot be destroyed, yet general relativity seems to allow it. Resolving this paradox is one of the central challenges in theoretical physics. The nature of time at the quantum scale, at the cosmic scale, and in the presence of extreme gravity remains an active area of research. Physicists continue to develop new theories and conduct experiments, seeking a complete understanding of time's nature. What began with Newton's simple definition has become one of the most profound and perplexing aspects of reality, a phenomenon that is simultaneously familiar and deeply strange, both the backdrop of our experience and an active participant in the unfolding of the universe. While physicists study time with equations and experiments, biologists have discovered that living organisms carry their own internal clocks, biological rhythms that cycle independent of any external timekeeper. The most fundamental of these is the circadian rhythm, a roughly 24-hour cycle that governs sleep and wakefulness, body temperature, hormone release, and countless other physiological processes. The term circadian comes from the Latin words circa, meaning around, and diem, meaning day. These rhythms persist even in the absence of external cues like sunlight. If you place a person in a room with no windows, no clocks, and no way to tell whether it is day or night outside, their body will continue to follow an approximately 24-hour cycle, though it may drift slightly longer or shorter than exactly 24 hours. The master circadian clock in mammals resides in a tiny region of the brain called the suprachiasmatic nucleus, or SCN. This cluster of roughly 20,000 neurons sits just above the optic chiasm, where the optic nerves cross. The SCN receives direct input from specialized cells in the retina that detect light, allowing it to synchronize the body's internal clock with the external day-night cycle. At the cellular level, circadian rhythms are generated by a feedback loop of gene expression and protein production. Certain genes are activated, producing proteins that gradually accumulate. When enough protein builds up, it feeds back to suppress the genes that created it. The proteins are then slowly degraded, allowing the genes to become active again, and the cycle repeats. This molecular clockwork takes approximately 24 hours to complete one full cycle. Nearly every cell in the body has its own circadian clock, not just neurons in the SCN. The liver has a clock that helps regulate metabolism. The heart has a clock that influences cardiovascular function. Even individual skin cells maintain circadian rhythms. The SCN acts as the conductor of this orchestra, ensuring that all these cellular clocks remain synchronized with each other and with the environment. Disruption of circadian rhythms has significant health consequences. Shift workers, who must stay awake during nighttime hours when their bodies expect to sleep, face increased risks of cardiovascular disease, metabolic disorders, and certain cancers. Jet lag, the temporary misalignment between internal clock and external environment that occurs when crossing time zones, causes fatigue, difficulty concentrating, and digestive problems until the body's clock can reset. Seasonal changes also affect biological time. Many animals, including humans, show seasonal variations in behavior and physiology. Some species hibernate, entering a state of profound metabolic slowdown that can last for months. During hibernation, body temperature drops, heart rate and breathing slow dramatically, and time seems to stretch. A hibernating ground squirrel's heart might beat only 5 times per minute, compared to 200 beats per minute when active. Migration is another phenomenon intimately connected to biological time. Birds that migrate thousands of miles between summer and winter habitats use multiple timing systems to know when to depart. They respond to changes in day length, which trigger hormonal changes that prepare them for the journey. Some birds also possess a magnetic sense, allowing them to navigate using Earth's magnetic field, adding a spatial component to their temporal awareness. Beyond circadian rhythms, organisms show patterns at different timescales. Ultradian rhythms cycle multiple times per day. The human sleep cycle, which moves through stages of light sleep, deep sleep, and REM sleep, repeats approximately every 90 minutes throughout the night. During waking hours, many people experience ultradian rhythms of alertness and fatigue, with peaks and troughs occurring throughout the day. Infradian rhythms take longer than 24 hours to complete. The menstrual cycle in humans, averaging about 28 days, is one example. Certain animals show longer cycles. The bamboo flowering cycle in some species takes decades, with entire forests blooming synchronously only once every 60 or even 120 years before the plants die. The perception of time's passage also changes throughout the human lifespan. Children often feel that time moves slowly. A summer vacation feels endless. The wait for a birthday or holiday seems interminable. But as we age, time appears to accelerate. Years seem to pass more quickly. Decades blur together. This phenomenon has been noticed for centuries, and several explanations have been proposed. One theory suggests that time perception is proportional to one's age. When you are 10 years old, 1 year represents 10% of your entire life. When you are 50, 1 year is only 2% of your life. By this logic, each year feels shorter relative to the accumulated years already lived. The summer of childhood felt long because it represented a larger fraction of total experience. Another explanation involves novelty and attention. Children constantly encounter new experiences, new learning, new stimuli. The brain encodes these novel moments with greater detail, creating richer memories. As adults settle into routines, days become more similar, less remarkable. When looking back, periods of routine compress in memory, while novel experiences stand out and seem to have lasted longer. The neurological basis of time perception involves multiple brain regions. The basal ganglia, particularly the striatum, appear to be important for timing intervals of seconds to minutes. The cerebellum contributes to timing in the millisecond range, crucial for coordinating rapid movements. The prefrontal cortex is involved in prospective timing, the ability to estimate how long something will take, or to time an action for a specific future moment. Damage to these brain regions can impair time perception. Patients with cerebellar damage may have difficulty timing their movements smoothly. Those with damage to the basal ganglia, as occurs in Parkinson's disease, often struggle with interval timing. Some research suggests that dopamine, a neurotransmitter heavily involved in motivation and reward, plays a crucial role in the brain's internal clock. Drugs that affect dopamine levels can alter time perception. Stimulants like cocaine or methamphetamine, which increase dopamine signaling, often cause time to feel like it is passing more slowly. Users report that minutes feel stretched, that they can notice details they would normally miss. Conversely, marijuana, which has complex effects on multiple neurotransmitter systems, typically makes time feel like it is passing more quickly. Attention plays a central role in how we experience duration. When we are absorbed in an activity, time seems to fly. This state, sometimes called flow, occurs when challenge and skill are well matched, when we are neither bored nor anxious, but fully engaged. Hours can pass in what feels like minutes. Afterwards, the memory of the period may seem brief, because few distinct moments stand out. The experience was smooth and continuous. In contrast, when we are bored or waiting, time drags. Every second seems to last an eternity. The watched pot never boils, as the saying goes. The difference lies in how we are directing our attention. When waiting, we repeatedly check the time, noting how little has passed, which paradoxically makes the experience feel even longer. Fear and danger also distort time perception. People often report that during a car accident or other sudden emergency, time seemed to slow down. They could notice details, think multiple thoughts, perceive the unfolding event with unusual clarity. This effect, sometimes called time dilation, though it is not related to the physical phenomenon described by Einstein, may result from enhanced memory encoding during high-stress situations. The brain records more information per unit time, and when we recall the event, the density of memories makes it seem to have lasted longer than it did. Studies have attempted to measure this effect objectively. In one experiment, researchers had participants experience a frightening but controlled event, free falling into a net from a height. During the fall, participants wore a device on their wrist displaying numbers that alternated too quickly for normal perception. The idea was that if time truly slowed for the falling person, they would be able to read the numbers. They could not, suggesting that time did not actually slow perceptually during the event, even though retrospective accounts claimed it had. Memory is intimately connected to our sense of time. Without memory, there is no past, and without a sense of past, time loses much of its meaning. Patients with severe amnesia, unable to form new long-term memories, live in a kind of eternal present. Each moment is new, but moments do not accumulate into a coherent sense of duration or history. Different types of memory exist on different timescales. Sensory memory holds information for a fraction of a second. The visual image of a scene lingers briefly after you close your eyes. Working memory, which holds information for immediate use, lasts seconds to minutes. You can remember a phone number long enough to dial it, but then it fades. Long-term memory, by contrast, can persist for a lifetime. The consolidation of memories from short-term to long-term storage takes time. Sleep plays a crucial role in this process. During sleep, particularly during certain stages of sleep, the brain appears to replay experiences, strengthening the neural connections that encode them. This is why a good night's sleep after learning improves retention. The brain is using time itself as a tool for memory. Psychological time is also influenced by emotional states. Depression often involves a distorted sense of time. Depressed individuals may feel that time is moving slowly, that each day is a burden stretching endlessly. They may also have difficulty imagining the future, a phenomenon called future time perspective. The future seems grey, empty, or unreachable. Conversely, mania, the elevated mood state seen in bipolar disorder, can make time feel accelerated. Thoughts race, ideas come rapidly, and the subjective sense is of time flying past. Sleep becomes less necessary, as if the internal clock is running faster, packing more experience into fewer hours. Cultural factors also shape how we think about and experience time. And clearly, some cultures are described as having a more monochronic view of time, where punctuality is highly valued, schedules are strictly followed, and time is seen as a limited resource to be managed efficiently. Other cultures take a more polychronic approach, where relationships and present interactions take precedence over schedules, and time is seen as more fluid and flexible. Language reflects these different temporal perspectives. Some languages grammatically mark past, present, and future with great precision, while others do not. The Hopi language, according to some analyses, does not distinguish between past, present, and future in the same way Indo-European languages do, though this claim remains debated among linguists. Even within a single culture, individuals differ in their temporal orientation. Some people are highly future-oriented, constantly planning, delaying gratification, and working toward long-term goals. Others are more present-oriented, focused on immediate experiences and less concerned with future consequences. Past-oriented individuals may dwell on memories, draw lessons from history, or feel constrained by what has already occurred. The ability to imagine oneself in the future, called episodic future thinking, appears to be connected to memory systems. Studies show that people with damage to the hippocampus, a brain region crucial for memory, also struggle to imagine future scenarios. This suggests that the same neural machinery we use to reconstruct the past is also used to construct possible futures, reinforcing the idea that our sense of time is deeply rooted in memory and imagination. Meditation practices often focus on time and temporal experience. Mindfulness meditation encourages practitioners to remain in the present moment, observing thoughts and sensations without judgment. Many meditators report that with practice, their subjective experience of time changes. The present moment expands, becoming richer and more vivid, while the usual rush toward the future or dwelling on the past diminishes. Near-death experiences, reported by some people who have been clinically dead and then resuscitated, often involve altered time perception. Experiencers describe their entire life flashing before them in an instant, or conversely, time seeming to stop altogether. Whether these experiences reflect actual properties of consciousness at the boundary of death or are artifacts of a dying brain remains unknown, but they illustrate how malleable our sense of time can be under extreme conditions. The biological and psychological dimensions of time reveal that time is not merely an external parameter measured by clocks. It is also an internal, lived experience shaped by biology, psychology, culture, and individual circumstances. The time measured by physics and the time experienced by consciousness are related but not identical, two aspects of a phenomenon that remains, in many ways, as mysterious to science as it is immediate to experience. The earliest mechanical clocks were not the small, precise devices we carry in our pockets today. They were massive public instruments, often built into church towers in medieval Europe. These first mechanical clocks, appearing in the 13th and 14th centuries, used a mechanism called a verge and foliot escapement, which allowed a falling weight to release energy in controlled increments, moving the clock's hands forward. These early clocks were not particularly accurate. They might gain or lose 15 minutes per day, but accuracy was not their primary purpose. They served to mark the hours for prayers in monasteries and to coordinate the activities of growing towns and cities. Time was being transformed from a natural phenomenon into a social and economic tool. The pendulum clock, invented by Christian Huygens in 1656, represented a significant improvement. Galileo had observed that a pendulum swings with a regular period that depends on its length, but not on the amplitude of its swing, at least for small angles. Huygens applied this principle to clockmaking, creating a timepiece that could keep time to within seconds per day rather than minutes. Pendulum clocks became the standard for precision timekeeping for nearly 3 centuries. Refinements were made, temperature compensation to account for the expansion and contraction of the pendulum rod with temperature changes, improved escapements to minimize friction, and careful attention to the clock's mounting to reduce external disturbances. By the 19th century, the best pendulum clocks could maintain accuracy to within a few hundredths of a second per day. The need for accurate timekeeping at sea drove further innovation. Determining longitude, a ship's east-west position, requires knowing the exact time. If you know that it is noon locally, based on the sun's position, and you also know what time it is at a reference location like Greenwich, England, you can calculate your longitude. 1 hour of time difference equals 15 degrees of longitude, but keeping accurate time on a rolling, pitching ship was extraordinarily difficult. Pendulum clocks did not work on ships. The motion disrupted them too much. In 1714, the British government offered a substantial prize, the Longitude Prize, to anyone who could devise a practical method for determining longitude at sea. The prize would go to a timepiece that could keep time to within 2 minutes over a 6-week voyage. John Harrison, an English carpenter and clockmaker, spent decades solving this problem. His solution was the marine chronometer, a spring-driven clock that compensated for temperature changes and was designed to resist the effects of a ship's motion. Harrison's fourth chronometer, completed in 1759, proved accurate enough to win the prize, though he had to fight for years to receive full recognition and payment. The development of railroads in the 19th century created new demands for time standardization. When travel was slow, each town could keep its own local time based on the sun's position. But when trains began moving people rapidly across distances, this patchwork of local times created chaos. A train schedule could not function if every station used a different clock. In 1883, railroads in the United States and Canada adopted a system of standard time zones, dividing the continent into 4 zones, each differing by 1 hour. The following year, at the International Meridian Conference in Washington, D.C., delegates from 25 nations agreed to establish a global system of time zones based on the prime meridian running through Greenwich, England. Time became a matter of international coordination. The 20th century brought even more precise timekeeping technologies. Quartz clocks, developed in the 1920s and 30s, use the piezoelectric properties of quartz crystals. When an electric current is applied to a quartz crystal, it vibrates at a very stable frequency, typically 32,768 times per second. These vibrations can be counted electronically to keep time with far greater precision than mechanical clocks. Atomic clocks, first developed in the 1950s, pushed precision to extraordinary levels. These clocks measure time by counting the oscillations of electromagnetic radiation emitted or absorbed by atoms when they transition between specific energy states. The cesium-133 atom, in particular, has a transition with a frequency so stable and reproducible that it has become the basis for the international definition of the second. In 1967, the second was officially redefined. It is no longer based on Earth's rotation or orbit, but on atomic transitions. 1 second is defined as the duration of 9,192,631,770 cycles of the radiation, corresponding to a specific transition in cesium-133. This definition allows scientists anywhere in the world to create a standard of time that agrees with extraordinary precision. Modern atomic clocks are so accurate that they would lose or gain less than 1 second over hundreds of millions of years. Optical atomic clocks, which use atoms that oscillate at much higher frequencies in the visible light spectrum, are even more precise. These clocks are so sensitive that they can detect the time dilation predicted by general relativity over height differences of just a few centimeters. Such extreme precision has practical applications. Global navigation systems like GPS rely on atomic clocks aboard satellites. Each satellite broadcasts a signal that includes the precise time the signal was sent. Your GPS receiver picks up signals from multiple satellites and calculates your position based on the tiny differences in the arrival times of these signals. An error of 1 microsecond in timing would translate to a position error of about 300 meters. Coordinated Universal Time, or UTC, is the time standard by which the world regulates clocks and time. It is based on atomic time, but is occasionally adjusted by adding or subtracting leap seconds. These leap seconds account for the fact that Earth's rotation is gradually slowing due to tidal friction. Without periodic adjustments, atomic time and the time based on Earth's rotation would eventually drift apart. The calendar we use today, the Gregorian calendar, was introduced by Pope Gregory XIII in 1582. It refined the earlier Julian calendar, which had been established by Julius Caesar in 45 BCE. The Julian calendar had a simple rule. Every 4th year is a leap year, with an extra day added to February. This gave an average year length of 365.25 days. But the solar year, the time it takes for Earth to orbit the Sun, is actually about 365.2422 days. The Julian calendar was thus about 11 minutes too long per year. Over centuries, this small discrepancy accumulated, causing the calendar to drift relative to the seasons. By the 16th century, the spring equinox was occurring 10 days earlier in the calendar than it should have. The Gregorian reform kept the leap year rule, but added exceptions. Years divisible by 100 are not leap years, unless they are also divisible by 400. So 1900 was not a leap year, but 2000 was. This adjustment gives an average year length of 365.97 days, much closer to the true solar year. The adoption of the Gregorian calendar was gradual and often contentious. Catholic countries adopted it quickly, but Protestant and Orthodox countries resisted for religious and political reasons. Britain and its colonies, including America, did not switch until 1752. By then, the discrepancy had grown to 11 days, which was simply skipped. People went to bed on September 2nd and woke up on September 14th. Different cultures have developed their own calendar systems, each reflecting specific astronomical observations and cultural needs. The Islamic calendar is purely lunar, consisting of 12 lunar months with no attempt to synchronize with the solar year. This means that Islamic months drift through the seasons, completing a full cycle approximately every 33 years. The Hebrew calendar is lunar-solar, like the ancient Babylonian calendar, adding an extra month in 7 out of every 19 years to keep the calendar aligned with the seasons. The Chinese calendar is also lunar-solar, with months beginning on the new moon and leap months added as needed. The Chinese New Year, the most important traditional holiday, can fall anywhere from late January to mid-February in the Gregorian calendar, depending on when the new moon occurs. The French Revolution brought an attempt to decimalize time itself. The revolutionary government introduced a calendar with 12 months of 30 days each, plus 5 or 6 extra days. Each month was divided into 3 10-day weeks. The day was divided into 10 hours, each hour into 100 minutes, and each minute into 100 seconds. This decimal time was intended to rationalize timekeeping, but it proved deeply unpopular and was abandoned after a few years. Timekeeping devices have become increasingly miniaturized and ubiquitous. Wristwatches, introduced in the early 20th century, brought personal timekeeping to the masses. Quartz watches, appearing in the 1970s, made accurate timekeeping affordable. Today, most people carry smartphones that synchronize with network time servers, ensuring that their clocks are accurate to within milliseconds. The synchronization of time across the globe enables modern telecommunications, computer networks, and financial markets. High-frequency trading, where computers execute millions of transactions per second, requires precise timestamps to ensure fair and orderly markets. Scientific experiments, from particle accelerators to radio telescopes, coordinate measurements using atomic clocks and GPS time signals. The history of timekeeping reflects humanity's desire to impose order on the flow of experience, to divide the continuous stream of time into measurable, manageable units. Each advance in precision has opened new possibilities, from navigation across oceans to communication across continents. Yet the question remains, are we measuring something external, an objective feature of reality, or are we constructing a framework that helps us organize our experience and coordinate our actions? The tools we use to measure time have changed dramatically, from water clocks and sundials to atomic fountains and optical lattices. But the fundamental challenge remains the same: to capture in numbers something that we experience as flow, to make concrete and countable something that slips constantly from present to past. Our measurements grow ever more precise, approaching what seems like a perfect description. Yet time itself remains elusive, always escaping complete capture, always exceeding our attempts to pin it down. In the end, all our clocks, no matter how accurate, are human creations. They tick and chime and display digits because we built them to do so. They tell us what time it is, but they do not tell us what time itself might be, independent of our measuring. That question, the deepest question about time, lies beyond the reach of any clock, atomic or otherwise, and perhaps beyond the reach of human understanding altogether. Yet we continue to measure, to mark, to count the moments, finding in this practice a way to navigate the current that carries us all from birth toward whatever lies beyond. Friedrich Nietzsche, the 19th century German philosopher, proposed a thought experiment he called the eternal return. Imagine that the universe has existed for infinite time and will continue to exist for infinite time. If there are only a finite number of possible states the universe can occupy, and infinite time for these states to occur, then every possible state must occur infinitely many times. This means that this moment, the one you're experiencing right now, has occurred before and will occur again, exactly as it is, infinitely many times. Your entire life, with all its joys and sorrows, its triumphs and failures, has been lived before and will be lived again, exactly the same way, eternally. Nietzsche asked, how would you live if you knew this to be true? The eternal return is not necessarily a claim about physics or cosmology. Rather, it is a test of one's relationship to existence and time. If you would welcome the eternal return, if you would say yes to living this exact life infinitely many times, then you have achieved what Nietzsche called amor fati, love of fate. You have accepted and embraced your existence fully. The idea of cyclical time appears in many philosophical and religious traditions. In Hindu and Buddhist cosmology, as mentioned earlier, the universe moves through vast cycles of creation and destruction. But in the Western philosophical tradition, time has generally been conceived as linear, moving from past through present toward future, with each moment unique and unrepeatable. St. Augustine, writing in the late 4th and early 5th centuries CE, offered one of the most profound meditations on time in Western philosophy. In his Confessions, Augustine asks, "What is time? If no one asks me," he writes, "I know what it is. But if I wish to explain it to someone who asks, I do not know." This paradox captures the peculiar status of time, intimately familiar, yet deeply mysterious. Augustine observes that we speak of measuring time, but what do we actually measure? The past no longer exists, the future does not yet exist, and the present has no duration. If the present lasted even a moment, it could be divided into past and future. So the present must be instantaneous, a mere boundary between what was and what will be. But how can we measure something that has no extension? Augustine's answer is that we measure time in the mind. When we remember the past, we are not perceiving the past itself, which no longer exists, but rather a present memory. When we anticipate the future, we are not perceiving the future, which does not yet exist, but rather a present expectation. Time, Augustine suggests, is a distension of the mind, an extension of consciousness that holds together past, present, and future in a single experiential field. Immanuel Kant, writing in the late 18th century, took a different approach. In his Critique of Pure Reason, Kant argues that time is not a feature of reality as it is in itself, but rather a form of human intuition. Time is the framework our minds impose on experience, the necessary structure through which we perceive the world. Just as we cannot see color without eyes, we cannot experience anything except in time. For Kant, questions about whether time is finite or infinite, whether it had a beginning or will have an end, are unanswerable because they apply concepts beyond the limits of possible experience. Time is neither a thing in the world nor a property of things. It is the form of inner sense, the way we organize our perceptions and thoughts. Martin Heidegger, a 20th century German philosopher, placed time at the center of his analysis of human existence. In Being and Time, Heidegger argues that human beings are fundamentally temporal creatures. We exist not as isolated present moments, but as beings who are always already thrown into a situation, past, engaged with present concerns, and projecting ourselves toward possibilities. Heidegger distinguishes between time as ordinarily understood, sequence of now moments, and what he calls primordial temporality, the deeper temporal structure of human existence. Authentic existence for Heidegger involves confronting one's own finitude, recognizing that death is the ultimate horizon that gives life its urgency and meaning. We are beings toward death, and this relationship to our own ending shapes how we understand and experience time. The arrow of time, the asymmetry between past and future, has puzzled philosophers as much as physicists. We remember the past but not the future. Causes precede effects. Entropy increases. Yet the fundamental laws of physics, with rare exceptions, do not distinguish between time running forward and time running backward. The arrow of time seems to emerge at the macroscopic level, but its ultimate origin remains debated. Some philosophers have argued that the flow of time, the sense that the present moment is special and that time passes, is an illusion. The block universe view mentioned earlier suggests that all moments of time exist equally. The flow is merely a feature of consciousness, not of reality. The presentist view, in contrast, holds that only the present moment exists. Past events have ceased to be, future events have not yet come to be, and the present is the sole reality. Growing block theory offers a middle ground. According to this view, the past and present exist, but the future does not. The universe is like a growing tree, with the present moment being the surface that divides what has become from what has not yet become. As time passes, more of reality comes into existence, adding to the block of past and present. Different cultures conceive of time in different ways, and these conceptions are often reflected in language. In English and many European languages, the future is often described as ahead of us, and the past as behind us. This reflects a common spatial metaphor for time. We are moving forward through time, or time is flowing past us from future to past. But the Aymara people of the Andes use a different spatial metaphor. For them, the past is in front, because it is known and can be seen, while the future is behind, because it is unknown and cannot be seen. This reversal illustrates that the spatial metaphors we use for time are not universal, but are shaped by cultural and linguistic factors. Mandarin Chinese sometimes uses vertical spatial metaphors for time. The word for last month literally means up month, while next month is down month. This vertical conception of time coexists with horizontal metaphors, suggesting that different spatial models can be applied to time depending on context. The way we think about time affects our behavior and values. Research in psychology has identified several temporal orientations. Future-oriented individuals tend to plan, save money, and delay gratification. Present-oriented individuals focus on immediate rewards and experiences. Past-oriented individuals may be either positive, drawing strength from happy memories, or negative, haunted by past regrets and traumas. Cultural differences in temporal orientation have been documented. Some studies suggest that people in industrialized Western countries tend to be more future-oriented, while people in some other cultures are more present-oriented. These are generalizations with many exceptions, but they point to real differences in how time is valued and experienced across cultures. The pace of life also varies. Cities are generally faster paced than rural areas. Certain countries, like Switzerland and Japan, are noted for punctuality and efficient use of time. In other cultures, relationships and flexibility are valued over strict adherence to schedules. Neither approach is inherently better. They reflect different priorities and ways of organizing social life. Modern technology has transformed our relationship with time. We live in an age of instant communication, where messages travel around the world in milliseconds. This immediacy creates expectations of constant availability and rapid response. The boundary between work time and leisure time has blurred for many people, as smartphones keep us perpetually connected. Some scholars speak of time compression or time famine, the feeling that there is never enough time. Despite labor-saving devices and increased efficiency, many people feel more rushed than ever. The acceleration of life's pace, driven by technology and economic pressures, can lead to stress, burnout, and a sense of being out of sync with natural rhythms. In response, movements promoting slow living have emerged. Slow food, slow travel, slow fashion all emphasize quality over speed, mindful engagement over hurried consumption. These movements represent a critique of the modern temporal order and an attempt to reclaim time as something to be savored rather than merely managed. Literature and art have long explored time's mysteries. Marcel Proust's In Search of Lost Time is a meditation on memory and how past experiences, seemingly lost, can be recovered through involuntary memory, as when the taste of a Madeleine cake suddenly transports the narrator back to childhood. Virginia Woolf's novels often play with chronology, moving fluidly between past and present, external events and interior consciousness. In visual art, time can be represented through sequence, as in comic strips or film, or through suggestion, as in paintings that capture a single moment, but imply what came before and what might follow. Photography freezes time, preserving a moment that would otherwise vanish. Yet the frozen moment in a photograph is always already past by the time we view it, making every photograph a kind of ghost, an image of what no longer exists. Music unfolds in time in a unique way. A piece of music cannot be experienced all at once. It must be heard sequentially. The temporal structure of music, with its rhythms, tempos, and patterns of repetition and variation, creates emotional effects that are intimately tied to our experience of time. A slow movement can make time feel expansive and contemplative, while a rapid movement can create excitement and urgency. Religious and spiritual traditions offer various perspectives on time and eternity. In Christianity, eternity is often conceived not as endless time, but as a state outside of time altogether. God, in this view, exists eternally in a timeless present, perceiving all of history simultaneously. Human life is temporal, but the soul may enter into eternity after death, participating in God's timeless mode of existence. In some mystical traditions, spiritual practice aims at transcending time, achieving a state of consciousness in which past and future dissolve, and only the eternal now remains. This eternal present is not the fleeting present of ordinary experience, but a spacious awareness that encompasses and transcends temporal distinctions. The nature of time also raises questions about personal identity. What makes you the same person over time, despite constant physical and psychological change? Is it memory, which links your present self to your past? Is it a continuous stream of consciousness? Or is the self an illusion, a story we tell ourselves about continuity, when in fact there is only a series of momentary experiences. Buddhism teaches the doctrine of anatta, no self. There is no permanent, unchanging self that persists through time. What we call the self is actually a constantly changing process, a flow of physical and mental phenomena. Clinging to the idea of a fixed self causes suffering because it denies the reality of impermanence. Western philosophy has often taken the opposite view, asserting the existence of an enduring self or soul. But some philosophers, like David Hume, have argued that when we look inward, we find only a bundle of perceptions, not a unified self. The self, in this view, is a construction, useful for navigating life, but not a metaphysical entity. Time travel, a staple of science fiction, raises fascinating philosophical puzzles. And clearly, if you could travel back in time and prevent your own birth, would you create a paradox? Or would your actions automatically be constrained so that the paradox never arises? Or would you create an alternate timeline, leaving your original timeline unchanged? Most physicists believe that backward time travel, if possible at all, would likely operate according to the principle of self-consistency. Any actions taken by a time traveler would already be part of history, so paradoxes would be avoided. Alternatively, quantum mechanics might allow for branching timelines, where each quantum event creates new universes, permitting a kind of time travel without paradox. Forward time travel, in a sense, is already possible. Traveling at high speed or residing in a strong gravitational field causes time to pass more slowly for you than for others. If you traveled in a spaceship at nearly the speed of light for what felt like a year and then returned to Earth, you might find that decades or centuries had passed. You would have traveled into Earth's future. As we contemplate time's nature, we find ourselves confronting questions that blend physics, philosophy, psychology, and culture. Time is measured by clocks, yet experienced by consciousness. It is described by equations, yet lived as narrative. It is universal, yet intimately personal. Perhaps time is not one thing, but many. Physical time, biological time, psychological time, cultural time, each with its own properties and rhythms. Perhaps the search for a single, unified understanding of time is misguided, and we must content ourselves with partial perspectives, each illuminating one facet of a phenomenon that exceeds any single framework. Or perhaps, as some have suggested, time is not ultimately real at all, but a construct, a useful fiction we impose on a timeless reality. We may never know with certainty. What we do know is that time shapes our existence profoundly. It gives structure to our experience, urgency to our actions, and poignancy to our fleeting moments. Whether absolute or relative, real or illusory, time is the medium in which we live, the current that carries us forward, the dimension along which the story of the universe, and our own small stories within it, unfolds and finds whatever meaning it may have.